we're going to learn about the 11 soil forming processes. But first, I just what's that? Well, it's a disc. Soil of the ages. I guess we're going to have to put this in and listen to it. What do you think, guys?
Sounds great.
Okay, let's do it. Cool.
He left yesterday behind him. You might say he was born again. You might say he found the key for every door. When he first came to the mountains, his life was far away on the road hanging.
One of the most important concepts in understanding soil genesis is the principle of uniformitarianism. The present is the key to the past. The Earth's surface is formed by slow, ongoing geologic processes that are active today as well as that were continually active years ago. So think about erosion of landforms, deposition of sediments, tectonic drift, volcanism. All those geologic processes that are occurring today were occurring hundreds of millions of years ago at the same rate, at the same scale as we see them today. And if we want to look at an example, see we have Mount Everest that we generally think of as the king of all mountain ranges ever in the world, because Everest is at like 29,000 feet. But if you apply this law of uniformitarianism, we could also look at the Great Smokies, the Appalachian Mountains, which, looking at this picture, seems to be, there just seem to be rolling hills, only a few thousand, or only like 3,000 feet above sea level. But actually, at one point, the Appalachian Mountains were almost believed to be as tall as Mount Everest in the Himalayas. And applying the law of uniformitarianism, the Appalachian Mountains formed 330 million years ago during the creation of Pangaea, when Europe and North America kind of collided, forming this huge mountain chain that was thought to be 29,000 feet high. But obviously, since that range formed 333 million years ago, processes like erosion have continued to erode down the mountains so much that you go from, say, 29,000 feet to only a few thousand feet. And this is the law of uniformitarianism at its finest. Another example of the law of uniformitarianism is when we're looking at the Grand Canyon. Prior to the man that founded the law of uniformitarianism, the principle of uniformitarianism, James Hutton, in 1785, prior to that, the Earth's surface was thought to be formed by catastrophic events, very kind of biblical things straight from the Bible. So take the Grand Canyon, for example. That was thought to be formed in the course of a few days from the Great Flood. But if you look at the rock and fossil record, you can see that the 6,000 plus feet of erosion from the top to the base of the canyon occurred over 5 to 6 million years ago, due to stream erosion of the Colorado River. This kept kind of eroding down due to lots of energy, and over the course of 5 or 6 million years, we eroded this huge canyon that we call the Grand Canyon today. Here are two examples of the principle of uniformitarianism at its finest. In general, I know we're talking about rocks here, but the same can be applied to soil. So soil forming processes that are active today have been operating at the same rate, at the same scale, over the past hundreds of millions of years.
When you were young and your heart was an open book, you used to say, live and let live. You know you did, you know you did, you know you did. But if this ever-changing world.
Today, man.
Doing
Good to
well.
talk to you. Good to
Nice
talk
to see you.
Yeah. So I kind of like to talk to you today. Do you know where we're at, kind of in the area? Are we in like a, what would you say, a floodplain, maybe?
Yeah, I definitely say we're.
Yeah. So like we're down here in this floodplain, and where this creek is eroded back. And I kind of want to talk to you today about forming and destroying processes of soil. So the way that this formed, kind of, is that as this creek once ran through here, it would have eventually, at one point, it would have been back over here on this back hill. And as it's moved and deposited soil on the outside of this curve, it's moved all the way back through and over into here. As you can see here, this soil is kind of newer, more foreign, just newly deposited, not a lot of structure going on right now, things like that. There's other ways that soil can be destroyed. So, for instance, there's human effects, but I'll talk about that later. But there's also some effects that occur naturally or unnaturally, like, for instance, the 100-year flood that occurred whenever Jeff City was flooded and things like that. And then also there was the Johnson shut-in, where that dam broke down there, and it eroded all that soil away that was down there by the shut-in. And that caused a lot of trouble for the local area because it took all the soil off of the top of the rock formation. And so you just kind of need to, just kind of helping you out on forming and destroying. You know, there's a lot of deposition that occurs in these soils, and it's always good to really kind of look and get to look at things like the creek and understand that, you know, that's what helps to deposit the soil. So, yeah, there's other ways soil can be deposited off of hillsides, things like that, help form. Soil will develop over time, will develop over time, maybe through weathering or some other effects that occur with the climate. And all in all, it kind of goes back to those 5 soil forming factors. But, yeah, it's good to get to talk to you today, man.
It's nice to see you.
Have a good one. Yeah,
Nice
good to see you too, bro. Good to see you too. Have a good one, man.
You're as cold as ice. You're willing to sacrifice our love. You never take advice. Someday you'll pay the price. I know. I've seen it before. It happens all the time. You're closing the door. You leave the world behind.
Hey guys, so today I want to talk to you about the 5 soil forming factors. For instance, in gellisols, one of the many 12 soil orders, it takes a very cold climate where permafrost is present up in the north of America, or up in the north of the North American continent, in Alaska, for instance, where these soils form. And it's because the climate up there is incredibly cold, and it allows for that ice layer to form in the horizons. This is categorized as one of the 5 soil forming factors, of which there are climate, the temperature, and the rain that occurs, organisms such as the biota that live in the area, the relief or the topography and slope of that area, the parent material which forms, such as loess or a residuum that forms within that part of the world. And then, of course, it ends with time to determine how aged that soil is within the area and determine how that soil, how long that soil's been there, and so that we kind of get an idea of what's went on.
If I could turn back time, if I could find a way, I'd take back those words that'll hurt you.
What do we have here?
Oh, let's check it out, Whitney. Alright, let's get a little piece.
Great.
What do you think we got? Are you sure?
I'm not.
Actually, we have a limestone here, and this limestone actually occurred due to processes no longer active today on the Earth's surface. So currently, this limestone is Mississippian age, so it's actually 325 million years ago.
Wow.
And we know that limestone traditionally form in shallow seas that are fairly warm. And so that would mean about 325 million years ago, central Missouri here was actually was under a epicontinental sea. So pretty much the continental sea is covering continental landscape. And so that's how we deposit this limestone.
Okay. Can you tell me how that relates back to soils?
So actually the same process in geology can be applied to soils in terms of processes no longer active on the Earth's surface can affect the soils and geology we see today. So, like I said, we're obviously in Missouri. We're no longer under a sea here.
Okay, yeah, obviously.
But in terms of soil, so obviously in northern Missouri, about 1.2 billion years ago, we were currently under. It was an ice age, so northern Missouri is covered by glaciers, and that actually scoured the landscape, so that removed a lot of the topsoil. So we have very young, mature soils, and obviously, it's no longer active because we no longer have glaciers in northern Missouri.
No, we don't.
And in terms of understanding how soils in the same place can change over time, is that obviously location can actually change over time. And when we're talking about the same locale, we're talking about like the same area. So let's say like central Missouri, for instance.
Okay.
And so obviously in northern Missouri, we're glaciated. We remove that topsoil. And we have much younger soils in northern Missouri as opposed to go to southern Missouri, say like Van Buren or something like that.
Oh, those are old, yeah.
They are old because, you know why?
Can you tell me?
They were actually they're 1.2 billion years ago, or million years ago, excuse me. During the last glacial ice age, the glaciers actually only extended into Boone County as opposed to southern Missouri. So you are correct. In southern Missouri, we do have much older soils. So in the same general locale, let's just say in central Missouri, central to southern Missouri, we can have different soils that are formed by different processes, no longer present today.
Wow, okay. Thank you for the enlightenment.
Listen, baby, ain't no mountain high, ain't no valley low, ain't no river wide enough, baby.
If you need me, call me, no matter where you are, no matter how far.
Don't worry, baby.
Soil succession in the same locale can change as time progresses. Let's take Death Valley, for example. When you think of Death Valley, you think of very hot, very dry alpha sol heaven. But actually only a few million years ago, that wasn't actually always the case. Paleo records indicate Death Valley actually had a much less arid environment and was home to many perennial lakes. Lake Manly in particular, which actually was a few hundred feet deep. So what happened in the past few million years to make Death Valley one of the driest places on Earth that only gets 2.36 inches of rain a year? What happened was what we call the rain shadow effect, or pretty much giving rise to a mountain range. So what happens, the rain shadow effect is pretty much describes how precipitation and weather, how it changes as it goes over topography. So obviously we have a water source, we have water that evaporates, we have hot, moist air, and we're going up a grade, we're going up some topography, we're going up to a mountain, and as we're increasing in elevation, we have less atmospheric pressure with altitude, and as we get higher and higher up, eventually the air expands and cools rapidly, and pretty much all the precipitation falls out on the windward side of the mountain. And then as the wind continues to carry the system over the mountain, obviously we go down with the topography, where decreasing altitude, increasing atmospheric pressure, so the air is now very dry, fairly warm with no water vapor. And so on the other side of a mountain range, you're going to get what we call a rain shadow, and rain shadows generally form deserts. So in Death Valley, like I said, only a few million years ago, they had perennial lakes. So what really happened? The Sierra Nevada is actually what happened. When you think of the Sierra Nevadas, you think of Mount Whitney, which is the highest point in the continental United States at 14,500 feet. And about 20 million years ago, that's when the Sierra Nevadas really started to gain some elevation, along with some other fault-bound ranges between the Sierras and Death Valley. And as we can see, as we are going over the topography, we have the Sierras on the west, we got to cross over the Sierras, and so we still have a bit of moisture there, That's why we still have Owens Lake. That's why it's not a playa lake yet, like you have in Death Valley. And after you go up and down Owens Lake, maybe pick up a little bit more precipitation, you have to go over the Inyo mountain range. And then once again, the rain shadow effect, what we call the orographic effect, orogenic effect, excuse me, compounds on itself. And after it gets up and down Sierras, up and down the Inyos, it has to go up and down the Panamint Ranges. And every time the moisture system, the weather system, has to go up and down the range, it's losing less and less moisture, becoming a lot more arid. And that's the case in Death Valley. And so kind of a profile view, you have Mount Whitney here on the right, 14,500 feet. And so you have to go over that huge range and go back down and then over the Inyos, and you have a little bit of depression, and you got to go over the Panamint Ranges to then get Death Valley. And that going over those three ranges compound on itself. That's why Death Valley is one of the driest places on Earth, only getting 2.36 inches of rain a year. Another example of how soil succession in the same locale can change over time is in glacial settings. So when you have glaciers have one of the most great erosional power as they scour the landscape. So here we have an alpine glacier on the left, alpine glacier on the right, and a Piedmont glacier on the left, or continental glacier. And anyway, as they travel over the landscape, they scour the landscape. They're picking up everything they can, eroding everything by like thaw, abrasion, plucking, all that good stuff. That's how we get these glacial striations here. And obviously they're picking up pieces of bedrock. And not only are they picking up pieces of bedrock, they're also picking up the top layers of the soil profile. So say before you had a glacial event, you had a fully developed soil profile, very mature. You have a glacier that comes through. We're pretty much chopping the whole top layer off of our profile, and eventually the glacier is going to recede, and then we have an influx of new parent material, of glacial erratics potentially, as well as glacial till, as we have in the bottom left here. Here's a female for scale. And that new influx of sediment and us taking half the profile away almost resets us back to square one of soil development. So in both cases of how soil succession changes in the same locale as time progresses, you're going to have a change in parent material as well as potentially a change in climate of things of that variety. The time scale for soil formation is on the range of hundreds to thousands of years. Compared to biological species, soil formation is much longer, but pales in comparison to geologic time. The oldest soil recorded is loosely 2.5 million years ago. Let's compare it to the age of the Earth, at least since the development of complex multicellular organisms in the Ediacaran.
Take it easy.
estimation of modern plate tectonics only covers the last 60 million years, while the Earth is roughly 4.6 billion years old. To help put that into perspective, here are some more concrete analogies. So if we want to think about geologic time in terms of a calendar year, so obviously the Earth was formed on January 1st, so that's 4.6 billion years old. To kind of put soil in reference here, soil is 2.5 million years old, so that's like the Pleistocene Ice age, and that's December 31st. So the oldest soil only accounts for 1 over 365 of Earth's history, while humans legitimately only make up 1 minute of Earth's history. Another analogy we could look at would be a 24-hour clock. Everyone wants to look at dinosaurs. Dinosaurs, obviously, they died in the KT extinction, so that was like 66 million years ago. And 24-hour clock, that would be 10:56 p.m. While humans have only walked on this earth for 77 seconds. So human impact doesn't really make up too much of geologic time. And then if you want to put it into like a distance measurement, so let's say a football field, we're starting at the goal line. Dinosaurs are on the opposite 2-yard line. So remember, that's like 66 million years. Modern man would be at the 1 pin line, which obviously is very small. So that would be a few thousand years old. While the Industrial Revolution, which started in 1760, would be on 1/10 of the human hairline. So just to kind of recap, humans haven't really been on this earth long at all, as well as soil. Even the world's oldest soil, it pales in comparison to modern geology. Genesis is complex. Some processes are spasmodic and disrupt soil features formed by processes that are rather continuous over time. So say we were living in Jeff City in the early 90s, have a nice farm right in the Missouri River floodplain, have some really great soil for agriculture, has a nice thick deposit of silts and clays from the yearly flooding that you expect to get that very fertile farmland. And then in 93, guess what happens? You have that spasmodic 100-year flood that disrupts your soil development that was deposited over your traditional flooding events. So what happened in 93 was a 100-year flood. So you had a great influx of discharge in the river. The river flooded its levees into the floodplain, and obviously had a lot of energy, so it picked up all the silt and clays, put that in suspension off your farmland, deposited it way down the road, and instead, with all the energy, instead of having all that nice rich clay and silts there, you potentially have many upwards of 20 feet of sand deposited in your once prime, beautiful Missouri River floodplain. What are you going to do?
Another one of our 11 soil forming processes are soils or sites of clay formation and primary mineral weathering.
Okay.
So-
Tell me about that.
So kind of what we have going on here, obviously here in central Missouri we have our carbonate bedrock here, and actually in this case we have dolomite.
Okay.
And dolomite is kind of like your traditional limestone. So limestone, you think about, you have to have 80% calcium carbonate, the 20% other things, or other like sand, silt, and clays in there. But here we have our dolomite. So instead of having 2 calciums in there, we have some calcium and magnesium. So
Okay.
we have our dolomite bedrock, which is actually slightly more resistant to weathering. Do that magnesium on top, magnesium layer on top. And so obviously to get our dolomite deposited here, dolomite is a carbonate, so we had to be under some, at this point, probably 300 million years ago or so, we were actually under a sea right here, so that's how we formed our dolomite. And so it's kind of what's happening here to form this soil. So we have our dolomite bedrock, and actually our bedrock here has been eroding in place. So actually, when we're looking at their soil here, we actually have residuum as our parent bedrock. So what's kind of happening? We have our dolomite here as our parent material bedrock, and so what we have happening, we have our dolomite here. We're weathering it in place, and we're producing saprolites. I think that's what we got going on here, right?
Kind of. There's some rocks kind of breaking down off of this main mineral right here. I'm kind of seeing some granular stuff occurring where it's kind of weathering down into clays, like residuum is. Okay.
Yeah, that's perfect. Yeah, that's exactly what saprolites are. So we have our saprolite forming here. So kind of our bits and pieces of unconsolidated rock fragments.
Okay.
And then above it, we have accumulation of clay. We have this nice clay. And it's kind of red, isn't it?
Yeah, really red.
Do you know why that
Seems
might
pretty
be?
red to
No,
me.
no idea.
So it's actually red due to the magnesium
Okay.
within our dolomite as we weather. It kind
Oh my God.
stains it as we oxidize.
Okay. All right. Well, hey, thanks, Will. I really appreciate it.
Good stuff.
Yeah. So, one thing that we really need to touch on is this last process, and it's the effects that humans have on soil formation. Here, if you look around, we're here at the Basket Research Center. And something that some people really don't know is that this place used to be farmed. It was plowed. They took these hills, steep and unwieldy with little structure, and then plowed them, causing massive amounts of erosion. If you look underneath me here, you can even see, kind of, if you weren't on camera and you were a little closer, you can see that there's just a really thin layer here where it might have one day been much thicker. As you look and you go into these different things in life, we need to actually think about what occurs, what humans are doing to the environment. We need to look at situations like this and say, guys, that isn't the right idea. You shouldn't go out and do these things. And above all else, if you take anything away from this video, always know to look forward and that not to necessarily not make mistakes, but to try to make better choices. Because this soil, it can take thousands, millions of years to form, as we've talked about previously in the video. But what it can take to destroy it can happen in a matter of moments. And if anything else you take away, make sure to be good stewards of the land and always make sure to preserve what's happened with these soils. Just as the Romans fell, just as food scarcity has plagued many nations before, it can happen to us if we don't take care of the natural resources that we so desperately need to survive. And I'd just like to say thank you for watching our video, and above all else, remember to always go out there and do what's right, and to preserve the very soil which has been the rock of our ages. This disc and the music that we thought about today, it's really taught us something. And it's really made us think, what are we going to do for the generations to come? So I think that we need to leave this for the next group, so that whenever they come, they'll have it so they can think of it too. Have a good day, guys.
A singer in a smoky room, the smell of wine and cheap perfume. For a smile they can share the night. It goes on and on and on and on. Strangers waiting up the